All right, I think we can get started. So hello everyone, welcome to Ethics Seminar Series. I'm John, the seminar coordinator, and together with me is Ms. Kathy Manley. She is our communication specialist. And today, Kathy and I will be the moderator. Well, excited to have our speaker, Dr. David Nolan, joining us from University of Miami. A few things before we start. So just so you know, this seminar is being recorded and will be later published on our YouTube channel. Please feel free to ask questions through chat, or you can raise up your virtual hands so that we can unmute you. So let me give a brief introduction about the speaker. So Dr. David Nolan is a professor and chair of the Department of Atmospheric Science in the Rosenstiel School of Marine and Atmospheric Science and University of Miami. He earned his BA in physics and a PhD in Earth and planetary science from Harvard University. After research position at UC Berkeley, Colorado State, and GFDL, he joined the faculty at Rosenstiel in 2002. He has published over 80 journal articles on the dynamics and impact of tropical cyclones, the structure of the intertropical convergence zone, tornadoes, and other topics. In both 2016 and 2020, he and his co-authors earned the AMS Banner Miller Award for papers and contribute to improvement in tropical cyclone forecasting. Well, let's welcome speaker and Dr. Nolan, please proceed.
All right, thank you. You hear me now, John?
Yes.
Okay, excellent. All right. So you can see from the title of the talk, I'm going to be talking about gravity waves that are coming out of tropical cyclones. This is work I've been doing over the last 4 years or so with my collaborator Jun Zhang, who is a scientist at CMIS and the Hurricane Research Division here in Miami. And also some of this work I had help from Matthew Underlindy, who's my former PhD student, who is now at the Hurricane Center. And this work is not connected to his work at the Hurricane Center, but it's from computer simulations he did for me when he was my student. And this work is supported by a grant from the National Science Foundation. So before I start talking about gravity waves, I just want to tell you a little bit about the Rosenstiel School where I work. So let's see. Here we go. Okay, here's a picture of Florida. And most of you probably know where Miami is, and the Rosenstiel School is down here in Miami. But if you do a little close up on Miami, the overhead shot here from Google Maps, you can see the Rosenstiel School, as marked by the flag here, is actually on this island in the bay. So the University of Miami, where all the students are, or most of the students, is over here, in Miami. And John, can you guys see my cursor moving?
Yes.
Okay, good. So over here on the left, you see the University of Miami is over here in town. But the Rosenstiel School is over here on this little island, and if we get in a little closer, we get this nice overhead shot of the Rosenstiel School. It's on this man-made island called Virginia Key, and if we get in really close, we get this nice shot of the Rosenstiel School, which has actually been upgraded by the university quite a bit over the last 15 years. And you can see we actually have like a little beach here, which we can access, and there's a pier, and there's the ship owned by the university. There's a cafeteria here, a nice little view of the water. And you might also notice there's a pool. And you might wonder why, if we have a beach, we also need a pool, just like, every luxury hotel has a beach and a pool. But the reason actually is this pool was built to train scuba diving. So actually it's to train scientific scuba diving. For example, there's people at the Rosenstiel School whose job is to go out in a little boat and dive in the ocean and count fish, which is pretty cool. And they want to teach people how to count fish while they're doing scuba diving, and so that's what this pool was built for. And you can't really tell from the shot, but it's actually 15 feet deep all the way around. It's like this, super deep pool all the way around. So this is the Rosenstiel School. Now let me give you an outline of what we're going to talk about today. I'm just going to give you kind of a first look at these radiating waves. I'll just go back and talk a little bit about research in the past on gravity waves and tropical cyclones. I will show you the waves as seen in hurricane simulation, and then I'll show you observations of the same waves, and then we'll use a linear dynamical model to try to understand the waves, and then at the end I'll talk a little bit more about our efforts to find more observations of these waves. Okay, and I'll start out my talk with a disclaimer, because we're not going to be talking about gravity waves in the stratosphere today. If you look in the literature and you look at gravity waves, you'll find that probably 60–70% of the articles on gravity waves in the atmosphere are related to gravity waves in the stratosphere, because gravity waves are very important for the dynamics of the stratosphere. And these are two illustrations of gravity waves. These are temperature anomalies caused by convection of the United States, and you can see these like almost kind of spiral wave type features like we're going to be talking about today, but these are not caused by a hurricane. These are caused by thunderstorms. And these are waves way up in this above the stratosphere, actually 85 to 95 kilometers, is probably caused by Hurricane Matthew. You can see these little these bands here propagating away. So we're actually going to be looking at gravity waves, basically down here where we live in the troposphere. So to give you an idea of what we're talking about, this is a visible satellite image of Typhoon Moranti taken by the Himawari satellite a couple years ago. And I'm going to play this little movie here. And what I want you to look for is these spiral features kind of radiating out of the top of this storm. And it's a little tricky because the storm actually has an outflow, right? So air is actually flowing away from the top of the center of this hurricane. But if you look carefully, you can see on top of that little bands, there's a good one sort of whoa, it's not supposed to happen. I'll see if I can pause this. All right, I just have to make sure I'm on the button here. No? Okay. So look for the spiral waves radiating out about right there, those waves there. That's the kind of waves we're talking about. There are these embedded on top of the outflow. There you can see them there, some of these waves kind of shooting out here. There's waves radiating out on top of the storm. And those are waves at the top of the storm about 12 to 15 kilometers in altitude in the outflow. So this is just an example of sort of the structure, right? We have a hurricane, we have an eye, we have stuff swirling around here, and then there are these waves radiating outward. They're very hard, they're pretty subtle here in these visible images, but I'll show you better evidence for them in just a few moments. So another way to see those particular waves is through computer simulations. So this is an animation made from a simulation of Hurricane Bill made using the WRF model by another of my PhD students, Yumin Moon. The simulation of Hurricane Bill. And this is a kind of a standard hurricane simulation which uses nested grids. And the inner nest has 1 kilometer horizontal resolution, very large domain, and the data was saved every 2 minutes. Now, there's a lot going on here. The red colors are upward motion, and the blue colors are downward motion. And you can see the convection in the hurricane around the eyewall is basically making very strong upward motions and some downward motions. But if you just sort of let your eyes relax, you can see these in the distance, sort of hints of these outward motions, spiral motions radiating outwards in the far field. So these little clusters here, those are the tops of thunderstorms. But these fast-moving features out here, those are the kind of gravity waves that we're going to be talking about today. The colors here are saturated, right? So it's hard to tell. Basically the colors only go from -2 to +2 meters per second, and that allows us to see these more subtle waves, even though it saturates the convection from the thunderstorms around the center of the storm. So a better way to visualize that is take that same simulation, and we draw a line, say, going directly southwest of the storm. We interpolate the data to that line, and then we can make a radius time Hofmüller diagram, right? So this is basically, this line here is this radius here, and then we're going forward in time. And so as these spiral waves propagate along this line, you can see them making these tracks along here in this simulation. And so you can see the gravity waves are pretty distinct from the spiral bands. The spiral bands are slow moving, and so that's why they move outward slowly. It's these features here. But the gravity waves move very fast and really, almost at a constant speed. Their speed is very constant. basically starting in the core and then radiating outward at a constant speed. And that speed, just eyeballing it from this diagram, is about 25 to 30 meters per second. Okay, so these are the kinds of waves that we want to talk about today. But let's go back and get some perspective on research on tropical cyclones, gravity waves. So in the very earliest three-dimensional computer simulations of hurricanes, such as those done by Rick Anthes and Kurihara and Talea, they actually found these band-like features. This is actually a picture from their figure. And I think the effective resolution in these simulations was like 100 to 200 kilometers, very, very coarse, and only a few vertical levels. Nonetheless, they got these spiral-like features, and they looked like rain bands. So they got very excited. It was like, hey, not only did we simulate a hurricane, but we actually got rain bands. But the problem was they were moving outward very fast. They were moving outward at a similar speed I showed you earlier, like about 30 to 40 meters per second. And so that wasn't really consistent with what spiral bands do, like the kind you see on radar, because they tend to move outward very slowly. Similarly, same Kurihara and also Hugh Willoughby, 1977, they derived instability mechanisms for spiral buoyancy waves and proposed those as a mechanism for spiral band formation. And this is a figure from Hugh Willoughby's paper. The problem was, as I was just saying, the waves, these waves move outward very fast, just like the waves that I show you here. They're moving outward 25 to 30 meters per second. And the spiral bands we see on radar basically only move out at a few meters per second, or don't even move outward at all. So there's a disconnect there, and eventually gravity waves it was decided they are not what caused spiral bands. Now, another interesting paper by Chow, Chan, and Lau, 2002, and a follow-up by Chow and Chan, 2003, they looked at spiral waves coming out of tropical cyclones in simulations, and then they used that to do an analysis in the shallow water equations. And from that, they deduced that gravity waves were carrying a significant amount of angular momentum out of tropical cyclones. And they proposed that maybe, this is part of the reason it's hard to predict tropical cyclones, because our budget for the angular momentum isn't very good because we're leaving out this important factor. But they actually estimated that 10% of the inner core angular momentum was being radiated outward every hour, which is a lot, right? I mean, if you had anything and you're losing 10% of it every hour, it's going to be gone very fast. So that result, well, it didn't make a lot of sense to me and some other people. And so with my former student, Yumin Moon, we published a paper sort of finding the opposite, that these waves exist, but they're not actually transporting very much angular momentum, almost nothing. And that was also confirmed in a paper by David Schechter and also by Eric Hendricks et al. 2010. So in these previous papers, what they had in common is they were trying to understand what role did gravity waves have in the physics of hurricanes. But what we're going to end up talking about, later in this talk is we're not going to try to understand what gravity waves are doing in hurricanes, but maybe they're telling us something. Maybe there's information coming from those waves out to us about what's going on in the hurricane. Okay. So let's go back to another simulation, right? So the first simulation I showed you was pretty cool, but it's very messy, right? So the nice thing about the modeling world is we can make a clean environment. And so I can set up a hurricane on an infinite ocean with no land or cold pools or cold fronts or synoptic weather systems, just this beautiful, perfect lake setting off to infinity of ocean water. And I can create a hurricane environment like that, and it's going to look a lot nicer and a lot cleaner. And so this is another, the inner core of another simulation like that. And this inner domain here is very large. If you're in the modeling business, 720 by 720 points of 1 kilometer grid spacing. Again, we save the model output every 2 minutes. And this is actually the winds at 700 millibars, which is what we call flight level. It's where the aircraft flies when it's in a hurricane. And again, we see this very nice hurricane, very symmetric, and these beautiful spiral waves propagating outward. So these are, a cleaner representation of the kind of waves that we're looking for. And one way, even a diagram like this is a little bit messy, but one way to clean it up is to do some filtering. So this figure up here in the upper left is the total vertical velocity at 700 millibars. And actually, I've added on this figure these gray contours. And those gray contours are where there's cloud, basically where there's convection. And I added those on this particular figure to show that these bands out here, which you can clearly see, are in completely dry air, or I should say not precipitating air. So the bands you see out here are not associated with convection or precipitation or anything propagating outward. They're just going through clear air. But we take that vertical velocity field and we do azimuthal wave number filtering, where essentially we basically do a Fourier series of the flow around the azimuth, and then we basically separate all the wave numbers, and then we sum back together only some of the wave numbers, and that gets rid of a lot of the noise. So, for example, if we take this and we do a Fourier transform around the azimuth of all the data, and then sum back together only wave numbers 2 to 5, then we get we can see these bands a little bit more clearly. Now, this is the same procedure, the result of the same procedure applied to the surface pressure. And you can see it also shows bands, which is not surprising. But if you look carefully, they're not the same bands. So you can see like these bands here in the vertical velocity at 700 millibars like have a certain pattern and certain radial wavelength. And these bands maybe at the surface and the surface pressure aren't exactly the same. They don't line up and they don't have exactly the same radial wavelength. And this figure here in the lower right is surface wind speed, and it's a little more like the surface pressure. So right away we're getting a hint that maybe there's different things going on at different levels, right? That we have seen different waves, whether you're in a plane at 700 millibars or whether you're measuring from the surface. And that's something we'll go back to several times in the talk. Another way to look at these waves is to make a vertical slice through the hurricane. This slice, north-south slice right through my idealized hurricane. And if I just do a little poor person's animation here, you can see the waves going out, or I'm going backwards now. So these waves are also propagating outward. And it would be nice to try to get a better understanding of the vertical structure. So what we can do is a little trick where we basically just draw a line here. This line is exactly 200 kilometers south of the center of the storm. And we use that to make a time series of vertical velocity as a function of height and a function of time. And then if we take that time series of W and compute empirical orthogonal functions, we can diagnose the predominant vertical structure of these oscillations. And that's what's shown here. So this figure on the left shows the first EOF, the dominant EOF, of these vertical motions propagating out of this hurricane. And you can see there's a peak here about 12 kilometers, just like you can kind of see right here. And then basically there's a vertical structure to this mode. And the red X's here are basically the pressure anomaly at each height regressed onto the principal component of that EOF, the time series. So basically, how does the pressure correlate with this particular EOF? And what you can see for this one on the left is there's a big signal at the surface. So this mode here, which is a sort of a wave number, sort of first baroclinic mode, first baroclinic wave mode in the vertical structure, has a pretty strong signal in the surface pressure, whereas the second EOF, which is a lot weaker, has a much higher vertical wave number and also has a much weaker signal at the surface. So that's kind of similar to what what I was just showing before. That there's a deep mode with a strong pressure surface, and there's also a different mode which has strong motion vertical velocities in the middle levels of the atmosphere, but very little signal at the surface. And that's kind of what we saw before, and we'll even see that again. Okay, so how can we observe these spiral waves directly? Well, one is with an airplane, right? So this plane on the left, this is the NOAA P3, which does lots of amazing stuff and very frequently flies through hurricanes. The standard pattern when you fly into a hurricane is called the figure 4, or sometimes it's called the alpha pattern, where you fly straight through the storm, make a left turn, let the wind accelerate you downwind to here, and you make another left turn and go back straight through the storm. So when you're doing that, sometimes you're flying towards the storm, and sometimes you're flying away from the storm. Let's see what that data looks like. So these are time series of vertical velocity measured by the P3 as it went through Hurricane Francis during the Sea Blast project in 2004. Now it's interesting, there's hundreds and hundreds of flights like this, but to get good vertical velocities, you have to calibrate the instruments at the beginning of the hurricane season. And it turns out they didn't do that every year. So we actually had to go back all the way to 2003 and 2004 to get reliable vertical velocities from the P3. But we do have them for some hurricanes, and Francis and Ivan are examples. So basically, you're flying in the plane, and you're feeling little up and down motions. Okay. Now you can look at this figure and say, "Oh, okay, I see a wave there. Maybe it's got a certain wavelength." This is actually in distance, not in time. But the problem is the waves are also moving, right? So we go back to this figure here. You're flying into the storm, and the waves are coming at you, so the waves seem faster. That's the Doppler shift. Or when you're flying this way, you're flying with the waves, so the waves seem slower. And if all you have is that one measurement, you can't know what the speed of the waves are. And if you can't know what the speed of the waves are, then you can't even know their wavelength either. All you can know is the frequency of your measurement, but you can't independently know the speed and wavelength of the waves. So that's our problem here. But some of them are going inward, and some of them are going outward. So if you calculate, basically you do a power spectra of data like this, and you separate it into the outbound legs and the inbound legs. And so the red, this is the average spectra over all the outbound legs. And you can see there's a peak here, let's see, around 7 or 8 kilometers. And then the blue is the average over the inbound legs. You can see there's a peak here around 3 or 4 kilometers. So basically, as we would expect, as you're going inward towards the hurricane and the waves are coming at you, the waves seem shorter. And when you're going outward, the waves seem longer. But if you assume that phase speed is the same, then you can basically set the two equations equal to each other, or take the two equations for the frequency and set the phase speeds equal to each other, and you can solve. And you can actually get separately the wavelength and the phase speed. So we find from these analysis that the phase speed of the outward going spiral waves is about 22 meters per second. And that's consistent with what I showed you before in the numerical simulations, which found 25 to 30 meters per second. And the typical wavelength is around 5 or 6 kilometers. Okay. Now, it would be nice if we had surface observations of radiating waves coming out of tropical cyclones. And if we wanted that, what we would need would be like research quality surface measurements from a fixed point. And it would be great if we had those measurements for long enough so that many hurricanes went by. Let's just say over the course of a single hurricane season. And if you really wanted to do this right, you would have to have surface pressure and wind speed every 10 seconds for several months. So that would take a lot to meet all these criteria. It would basically, you'd have to do like a field program to get that kind of information if you wanted to make surface observations of these radiating waves from tropical cyclones. And that would be really hard, except somebody already did that. They weren't looking for gravity waves. They were just measuring turbulence and air sea fluxes in hurricane season. And that was in the ITOP program, intensity of typhoons in the Pacific or something like that, our observations in the Pacific. And they had this special buoy, which is actually built here at Rasmus. And they took it out here in the Pacific, and they stuck it basically in the sweet spot of the typhoon zone, left it there for 3 months in 2010. And this figure is from a paper by Potter et al., which documents some of the results of this study. And fortunately, these 4 typhoons came reasonably close to the buoy over that period of time. So they had no idea, that they were looking for very, very high frequency. They were looking at turbulence in the boundary layer, and so they had very high frequency measurements, and they look kind of like this. So these are time series from that instrument, right? So this is 10-meter wind speed, and this is the pressure at 10 meters. And these 2 figures on the left are a day when there was no tropical cyclone. So, right, so calm winds, right, 5 meters per second, and there's some noise. And the same thing for the pressure. Now, when Typhoon Chaba, which was this storm here, was passing by. Actually, it wasn't that close. It was about 300 kilometers away. So you can see the winds were higher, but then there was a lot more noise, right? So if you take these 2 time series and you do power spectra, well, you get a lot of noise, a lot of red noise. But then down over here in the longer periods, there's actually a peak around 1,000 seconds. And similarly, in the pressure field, you also have something. You also have a peak at 1,000 seconds, and you have another peak here, like 2 to 3,000 seconds. So there is a signal of something with the periods, of around 20 minutes and periods of around 60 minutes in the surface pressure fields, surface pressure and wind fields around typhoons in the Pacific. And these are examples. So from whether Fanapi or Megi or Chaba, almost all of these have some kind of signal either at around 1,000 seconds or 2 to 3,000 seconds or both, whether it's in the pressure field or in the wind field. So we have evidence for these waves passing by overhead directly from surface measurements. Okay. So now we're going to talk about trying to understand these waves, and for that we're going to use this dynamical model. I'm going to go back to this simulation that I showed earlier. And I just want to stop for a minute. John, are there any questions so far?
No, not yet.
Okay, all right. I'm sort of reflexively going really fast because I'm always afraid of running out of time. So anybody out there, I'm going too fast. Think of a reason, think of a question, and I'll slow down. So. Okay. Time. Yeah. Okay. So this is that same animation I showed you before. Now, what I didn't tell you is that even though it looks super symmetric, this simulated hurricane is actually moving. It's going 5 meters per second to the west or to the left on your diagram. And it's also experiencing some wind shear. So wind shear is the variation of the wind with height in the atmosphere. And experiencing a little bit of wind shear, just 2.5 meters per second or 5 knots. But that is enough to actually make the convection to be preferred on the north side, right? So the standard understanding of hurricanes is that when there is wind shear, convection will be enhanced on the downshear left. So basically, if the shear is from left to right here, then the downshear left is on this north side. And that is illustrated in these two classic diagrams, one from Howes et al. Review paper in 2010. So in this situation, he's describing a tropical cyclone, and you can see the upper level flow here is going from left to right, just like I was saying it is here in this figure. And so the convection, the black area, is the enhanced part of the eyewall, and updrafts are initiated in the entrance of that preferred region and maximize and then decay after they move out of that. And that's also illustrated in this figure from Braun and Wu, 2007, which is Scott Brown. And what he was saying is that not only do you have this preference for vertical motion on the downshear left side, but also that the initiation of those updrafts is associated with what we call meso vortices. There are these little vortices that rotate around. So you have this big vortex rotating around, and then that is made up of little vortices which are also rotating around. And so as they rotate into the preferred region, they trigger convection, which makes like a new thunderstorms, which basically maximize on the north side, or so the downshear left side, and then decay as they go around. So we have this idea that basically these asymmetry, not only is there a left-right asymmetry, but there's also a pulsing going on. And I can actually show you that explicitly with this diagram. So go back to this figure here. We basically do an azimuthal, we basically calculate the vertical velocity, or I should say the moist convective heating around the eyewall. Okay, and then we make that into a Hofmahler diagram. So this is going around the eyewall. This is the angle from east, like going around the circle like this. And this is time. And so as you can see, is you see these features going around and around and around. But you can see they get very strong when they're in that downshear left side, right? Because this is here. And then they decay. And sometimes they sort of survive through the weak region, and then they reinitiate in the strong region. So we have asymmetric vortices swirling around the eye, triggering convection in the favored region, and then turning off in the unfavorable region. And so our hypothesis is that it's this pulsing asymmetric pattern that creates the spiral waves that we're talking about today. So how can we show that? Well, we're going to try to basically reproduce, use that kind of this kind of asymmetric pulsing forcing and put it into a dynamical model. Okay, so is the radiating gravity wave field a response to these rotating and pulsing asymmetries? And can we understand those features? such as the apparent differences in W, which show high frequency, and the surface pressure, which shows the low frequency. We're going to use 3D VPAS, which is an acronym for three-dimensional vortex perturbation analysis simulation, which is a code in MATLAB that I started writing about 20 years ago, and amazingly still exists today. And basically what that model does is it takes the inelastic equations in cylindrical coordinates. We linearize them around a basic state vortex. We discretize them on a grid. We turn that into a linear dynamical system for each azimuthal wave number, including n equals 0. So basically, all the winds, basically the perturbation velocities are broken into wave number 1, wave number 0, wave number 1, wave number 2, and so on. That is turned into a state vector, and then we basically solve the evolution of the dynamical system with the standard linear dynamical model. And where this T here is a giant matrix with thousands of elements representing all the grid points. And I'll show you in a few minutes what this really looks like in practice. So as I mentioned here, there's a basic state vortex. You're essentially defining a reference state, which is a symmetric, frictionless, balanced vortex that looks like this. So with analytical functions, we create a wind field which looks like a hurricane. So this is radius, this is height, and here we can see the peak wind in my frictionless hurricane is 50 meters per second, max 50 here, at a radius of 50 kilometers, and the wind decays as you go out away from the center of the storm, and it decays with height in a somewhat realistic way. Then we use the laws of gradient wind balance and hydrostatic balance to calculate potential temperature perturbation, what's the so-called warm core, which is keeping this vortex in thermal wind balance. So in theory, if you stick this into a model and turn on the go button, it'll just basically sit there and spin forever. It won't actually because models have friction, but we have no friction in the basic state. This is an example of the forcing function. So basically, I'm imagining a heat source that looks like this. It's basically supposed to look like a thunderstorm updraft, and it's centered just inside the eyewall, and that is going to rotate around the center, but it's only going to turn on when it's in the favorable side. So I've turned it a little bit. Now the favorable zone is here on the right side, on the east side of the storm, just for convenience. And the way to think about it is that your heat source is going around and around, but it's pulsing. And every time it enters the favorable zone, it basically ramps up, reaches its maximum, and then ramps back down. And so the period of that forcing, we imagine there's two of these anomalies, and they're going around and around, but they only turn on each one only turns on when it enters the favorable region, the part of the eyewall that has a lot of convection. And so that results in this pulsation with a period, in this case, of 70 minutes. And these curves here, they're just analytical functions I made up using e to the minus t to the fourth, and adding it to itself over and over. So I just was basically making up some pulsing function, which represents what I think is happening in tropical cyclones. So also should mention, of course, anytime you're working with gravity waves, you have to worry about reflection. And so this area here shows the size of the domain, the model domain. And these gray boxes here show where you have damping zones to prevent wave reflection, so your gravity waves don't come bouncing back at you. Okay, so let's just do one pulse, right? Just one burst of convection in the eyewall on the favorable side. So this is vertical velocity at 6 kilometers on the left, and this is pressure at the surface on the right. And then as we go forward here, we're getting to the maximum here. This is basically the maximum heating. I should say, you see this pattern here is because we're basically summing over wave numbers 0 to 5. The way the model works is it works at one wave number at a time, and if you want to get the full solution, you have to go back and add up all the wave numbers, and we can do that. But basically, because we don't have an infinite number of wave numbers, we get this like residuals here on the left side, which really shouldn't be there, but they're very small. So as we go forward, and now we have our pulse in the convectively favored region, and we go forward, the pulse turns off, but boom, you see this production of waves which radiate outward in these very, may I say, cool looking spirals. And you can see there's this fast wave which goes out very quickly, and then behind it we get these high frequency waves which move quite slowly. So we can see that again. So basically, one pulse makes this big burst of waves with different frequencies and different wave speeds. Another thing that's interesting is that the most prominent response is actually on the opposite side of the vortex relative to the pulse. The pulse was over here, but because the hurricane is advecting everything around very fast, we actually see most of the wave amplitude existing on the backside, on the other side of the storm. Now we can also look at this for the vertical cross section through that backside. So here, this is again the response to a single pulse with a sum of wave numbers 0 to 5. And so we go forward, we can see that leading edge of that pulse propagating outward from the center. And then you can see behind it those high frequency waves, right? So now this is a vertical section. And so here you can see these higher frequency waves in the vertical velocity moving outward. Boom, like that. Okay. Another way to see these waves is these radius time Hofmüller diagrams, right? So again, if I were to look at the data along this line here, okay, and then turn that into a radius time Hofmüller diagram. This is a radius here. Yeah, this is at lambda equals 180, so back other side of the storm, the west side of the storm. So for example, this is vertical velocity at 3 kilometers altitude. And you can see that after the pulse occurs, which is about right here, then these waves propagate out. You get these initial waves, and then more waves, and then more waves, and so on. And the cool thing about using the linear dynamical model is now you can go back and pull apart the response and see which wave numbers contribute most. So this is the total, and this is the symmetric part of the response in vertical velocity. You can see it's very weak. But now we go to look at wave numbers 1, wave number 2, wave number 3. So we can see that most of the wave response in vertical velocity in the middle of the atmosphere is in the asymmetric modes. But on the other hand, if we look at the surface pressure, right? So this is surface pressure, radius time Hofmüller. We see this big signal radiating outward very fast. It's like 60 meters per second, followed by some weaker signals. And that has a very large amplitude in wave number 0. But then decreasing in wave number 2 and wave number 3. So for the surface pressure, most of that wave response, which you might measure at the surface, is caused by the load modes, basically the symmetric mode, and then also the wave number 1 asymmetry propagating outward from the vortex. Now you might ask yourself, like, why are we seeing this like multiple sets of pulses? Why are they generating these multiple waves, and why are they at successively lower speeds? Right, so for example, this is the wave number 3 response in vertical velocity. And if we can look at this, basically, I put this mask here because the amplitudes there are very large, so you're not distracted by them. But even if you get rid of that mask, you can still see that signal. And another thing that you might think would be happening is that there's maybe like a reflection of r equals 0, but you don't really see that either. Well, what's interesting is if you do the same experiment, but with a symmetric pulse at the center and no hurricane, you still get these multiple wave packets. So the point I'm trying to make is that this excitation of multiple waves with different speeds is not only because there's a hurricane. It's actually a fundamental behavior of waves in the atmosphere. And another way to illustrate that is through this figure. So this is a radius height cross section. If I do a symmetric pulse, basically of heating, at r equals 0, and with no hurricane, and the modes radiate outwards, we still see the same behavior where we have this leading deep mode, and then this is right. So this is like m equals 1, and this would be like m equals 2, and then basically higher and higher frequency modes behind that. So part of what we're seeing here is just a fundamental, basic part of the fundamental nature or way in which the atmosphere responds to heating, which is confined in the troposphere. And just like any really cool thing that you've ever discovered, someone discovered it before. This has been known for a long time. As I learned, as I started publishing this work, this is a paper from Brian Mapes, my colleague here, Brian Mapes, 1993. He showed that the thermodynamic impacts of tropical convection are mediated by these first and second vertical modes, right? So if you have a heat source in the troposphere, you create a lot of modes, but the first 2 modes is a leading mode, like I just showed you, kind of the Bohr mode, and then behind it is the wave number 2 mode. And also in the context of stratospheric dynamics, this is work by Joan Alexander and Jim Holton. And these are waves generated by, again, by finite depth pulse of heating. And they radiate outward, but they also, over time, you can see their vertical wave number is increasing with time. So part of what we're seeing is, we see the spiral patterns because there's a hurricane, but we see these multiple mode patterns because that's just a fundamental property of the atmosphere. Okay, so if we just repeat the pulse, boom, 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 basically have it go around and around, we create these spiral patterns, pretty much, quite similar to what we've seen in the numerical simulations. So this is a Hofmauer diagram just showing the pattern repeating itself. If you just basically pulse for a few hours, it goes into a steady state, and you basically see the same pattern repeating over and over. And this is just what I think is a pretty cool animation of those waves radiating outward with time from this repeated pulsing. Okay, so as I was saying, this steady pulsing generates this radiating wave field. So now what we can do is we can take our steady radiating wave field in our linear dynamical model, and then we can create a time series just as if we were observing, if we had an anemometer or a vertical velocity detector at that location. So the red curve here shows the vertical velocity at 3 kilometers altitude at this point. And you can see there's this very high frequency motions. And then the blue curve shows the pressure, the surface pressure at this point, or I should say pressure anomaly. And you can see there's kind of like two frequencies. There's the slow frequency and the short frequency. And those frequencies or periods are very similar to what we saw from observations. So this is not a power spectrum of this curve, it's a power spectrum from observations, the same one that I showed earlier. So again, it shows that this gravity wave field, which is generated by these low wave number convective asymmetries, which are rotating and pulsing, is consistent with what we see in the observations and the numerical simulations. But you have a high frequency signal associated with vertical velocity in the middle of the atmosphere, and a low frequency signal, which is associated with surface pressure anomalies, or the deeper wave, I should say, propagating outward at a higher speed. Now you might look at that and say, well, wait a minute, okay, maybe we could actually figure something out here, because if I create these same diagrams, but if I change the intensity of the hurricane, then I get a different frequency, right? Because the frequency of my pulsation depends on how fast those convective asymmetries are going around the center of the storm. And if the storm is stronger and they're going around faster, I get a faster pulsation. And that's what's shown in these figures. Especially if you look at the blue curves, you can see that as if I go from right to left, as I increase the intensity of my hurricane and my convective blobs go around faster and faster, then I get a higher frequency signal. So you could kind of say to yourself, well, hey, maybe I could actually measure hurricane intensity from a distance with a barometer by listening to these waves. And it's conceivable that's possible. The problem is that there's also a lot of other information that you wouldn't necessarily have. You actually need to know the number of Meso Vortices. What I showed you before assumes 2. There could be 3 or 4 or 5. You need to know their speed relative to the tangential wind, which I've assumed to be 75% based on the computer simulations, but that could vary. And you need to know the size of the eyewall, because that also controls how long it takes the asymmetries to go around. So you would have to have a lot of additional information, and if you had that additional information, you'd probably already know the intensity of the hurricane. But it's still fun to think about how we could maybe detect the intensity or information about hurricanes just using barometers from hundreds of kilometers away. Okay, so now we've gone out and tried to get some more observations of these waves. So there are these instruments here called WeatherSim. Basically, this guy at Florida State does this for fun. He really, as goodness is his heart, he distributes these instruments. And so there's one at my school, and it's just it's got an anemometer and a barometer, and it was here when Hurricane Matthew went by. So we got the data, and we'd actually asked them ahead of time to save the data every 1 minute. That's a problem. The most pressure data is only saved every hour. You really need at least every 10 minutes, and preferably every 1 minute to do this. So we got the data, and this is what the pressure anomaly looked like as Hurricane Matthew passed by, and we fit that to a polynomial and removed that to get the anomaly, and then we did a power spectrum on this, and lo and behold, look, we got a peak in this 1,000 to 2,000 second range, again showing the signal of these gravity waves passing overhead as Hurricane Matthew went by. This is a helicopter. It's hard to explain, but I'll try. The dean of my school, Ronnie Avasar, my boss, he was a helicopter pilot in the army in Israel, and he still flies helicopters. So he actually got people to donate money so that University of Miami could have a helicopter, and on front of it are these instruments, which actually measure wind speed and pressure anomalies and stuff like that. So we got the idea that maybe when a hurricane was going by, we could fly the helicopter and detect the waves and show that they were detectable from the helicopter. So when Hurricane Irma was coming, we basically flew the helicopter on this flight path right here. This tiny little red line is actually the entire flight path. Okay, now Hurricane Irma is very far away. And the reason is because Hurricane Irma was coming, he had to fly the helicopter out of town to safety. So we couldn't wait for the hurricane to get closer. We had to do it on Thursday, like 2.5 days before the hurricane hit. So that's all we could do. So we flew the helicopter like this when Hurricane Irma was approaching. And in case you're wondering, yes, it's an incredibly beautiful view from a helicopter at 7,500 feet, as long as you're not in the hurricane when the hurricane's still far away. And we got some results. So this is what we saw. So this is vertical velocity as measured by the helicopter. And again, we tried to do this Doppler trick, this Doppler shift trick, where we went towards the storm and away from the storm, so we could basically detect, basically get an independent calculation of the wave speed and the wave length. So toward Irma, and then away from Irma, and then toward Irma. And we basically did our power spectrum. And from the power spectra, we diagnosed that there was a wave speed of 12 meters per second and a wavelength of about 5 kilometers, which is pretty close to what I'd seen before from the P3 data. So I was actually in shock because I didn't think this was going to work. Right? It seems too far. Like, how can you measure gravity waves from a helicopter, 600 kilometers from the hurricane? But we didn't have our null case, right? We hadn't flown with no hurricane yet. So then in March, we went on this super clear day, beautiful weather, to basically make sure that when there's no hurricane or thunderstorms around, that we don't detect any gravity waves. And we did. And so we got data like this. And basically we flew in 4 different directions this time, like in a crisscross. And you can see in our power spectra, they all have like these strong signals at about the same wavelength. So it turns out our clear sky flight in March 2018 also found vertical oscillations of the same amplitude and with a similar wavelength. Why is that? Well, it turns out that basically it's very hard to fly the helicopter at a constant altitude. And so what you're seeing here, these red and blue lines going up and down, is because the combination of the pilot, my boss, the dean of the school, trying to keep the helicopter at a constant altitude, and then the helicopter just going up and down, basically makes oscillations with a period, which is what we wanted to measure in the first place. So, sad ending of this story is, as of now, we did not or cannot measure gravity waves with a helicopter. So, back to the P3. And it's like, I'm almost done to talk now, in case you're wondering. Basically what we did before is we estimated the wavelength and phase speed by comparing the average spectra from the inbound and the outbound legs. But that's a statistical approach, and what I wanted to do was to compute these values explicitly by flying back and forth across the same waves, right? So basically I wanted to fly a pattern like this, where you fly out from the hurricane, and as soon as you get to your furthest point, you turn around and fly back over the same waves. And you should see the same waves, and you should also see a wavelength difference, which is due to the Doppler shift, and you should be able to, calculate the actual wavelengths and speeds of the actual individual waves. Or we propose this path here, where basically you go out to some distant point and then just fly out and then fly back to your starting point. Well, something really amazing happened this year, which is they actually flew this pattern, which was, to me, it was like a miracle that they actually did this. But so this is in Hurricane Teddy, which was out in the Atlantic. This is one of the hurricanes that did not hit the United States this year. And this is the flight. These colors here are the wind observations of the P3. And you can see here they did our pattern. They got to this point and they went out, They turned around and went back. And so that's them actually flying the pattern that that my friend June and I actually made up like on a PowerPoint, you know, with a mouse. It was really incredible, you know, experience for me personally in terms of my career that someone actually did this. And then later this year in Hurricane Delta, which went on and hit Louisiana, the same thing. You can see this is the flight, and when they got to this point here, they went out, they turned around and went back in. So we're very excited about that. We haven't processed the data yet because that was very recently, but we're hopeful we'll get to see the same signals there. So, okay, that is the end of my talk. And please let me know if there are any questions.
Please feel free to ask questions, and we got two earlier questions. The first one is from John, and he asked, has anyone looked at the GOES 1 minute image to extract the gravity wave phase speed and wavelengths?
Not to my knowledge, we haven't done that. So the only thing that I've done is just, you know, sort of eyeball it from an image like this. This is actually an image in one of our papers, and here you can see these bands here. And I basically looked at subsequent images like this and like literally by eyeball, like measured the phase speed. But anything more precise than that has not been done yet. It could be done. It's hard though. I mean, just looking at this signal right here, you know, this image right here, I think it'll be tricky to extract the wave. But there actually, I shouldn't say that. There are people who do like truly amazing things with satellite data. So if anyone out there has any ideas about how to do something like that, you know, let me know and we could coordinate on it.
And the second question from Jie Gong, she asked, so I can interpret from your presentation that these gravity waves do not carry away momentum, but carry away information or entropy. Is that true?
So I would say they do carry out momentum, which is very, very small amount. The amounts that we were estimating is something like, you know, one part in 10,000 every hour or something like that. It's a very small amount. I guess what I'm saying is, but they are carrying information, right? Just like when, you know, your cell phone emits a signal, but the mass and the energy of the cell phone is not changing, but it's sending out a signal about what's going on in the cell phone. And so that's how we're trying to see these gravity waves as possibly carrying information to us without necessarily being an important player in the physical processes.
The third question from Anil Kumar, and he asked, have you performed WOLF LES partial scale simulation to capture these waves?
So the question is if I performed a WRF, large eddy, and what was the third part of that? Something
yes,
scale?
I think so.
So the highest resolution simulations that I've done along these lines, I've done, what I showed today had 1 kilometer grid spacing. I've done simulations with half that, so 500 meter grid spacing. I haven't gone down to large eddy simulation scales. So most people think, when people talk about large eddy simulations, they're usually referring to something like, say, 100 meter grid spacing. The problem is that it's incredibly computationally expensive. And in addition, there are large eddy simulations that people are doing of hurricanes, but usually that is confined to a very small area around the eye because it's just so hard. And in order to see the gravity waves, we actually need to have a really big domain. So to answer your question, no, and part of the reason we haven't done that is it's just not computationally feasible to do large eddy simulation and simulate a large enough area to see the waves propagating. What I do want to know is whether or not models can accurately capture the radial wavelength of the waves. So by observations, the radial wavelength of the waves is around 4 to 8 kilometers. In my simulations with 1 kilometer grid spacing, the radial wavelength is like 12 to 16 kilometers. So my 1 kilometer grid spacing has waves which are about 2 times as big. I've done simulations with 500 meter grid spacing, and they're close to the correct wavelength. So it appears that to get the correct wavelength in a hurricane of gravity waves in a hurricane simulation, you have to have horizontal grid spacing of 500 meters, which is doable to some extent, but even that certainly is not feasible in any kind of forecast or even like a significant amount, doing a significant amount of research. It's very hard.
Then another question from Zhonghu Xin. And he asks, can the outward velocity of the gravity wave be affected by the stability of environmental atmosphere?
Oh yeah, that's a good question. So I didn't show it here, but one of the cool things about using that linear dynamical model is that you can change the sounding. So the stuff that I showed earlier, used a typical sounding, what we call the Jordan sounding, which is a typical sounding for the tropics. But in the paper, which is published in Jazz in May, 6 months ago in Jazz, I did additional tests with a higher stratification and a lower stratification. And to your point, yes, when you have a greater stratification, the waves move faster, right? Because basically n, the Brun-Vital frequency, is in the gravity wave phase speed formula, and so it matches quite well. But the reality is that stratification actually changes very little in the tropics. The stratification in the tropics is almost always the same, everywhere. So yes, it's true they go faster or slower depending on the stability, but that stability varies very little.
So here is one question from Jinhu Yu, and he said, have you had any chance to find diurnal cycle of the gravity waves for a hurricane observed and matched with a simulation? Also, are the low-level gravity wave related with upper-level stratosphere gravity wave?
All right, just to back up. So the first part was about the diurnal cycle, right?
Yes.
Okay, so yes. And I didn't have time to mention it all here, but one of my graduate students here has actually published a paper on the role of gravity waves in the diurnal cycle. Her name is Rebecca Evans, and it's like Evans and Nolan 2019, I think. And so she took this same model here, my linear model, but she forced it with diurnal cycle-like forcing, basically heating in the solar heating in the cloud anvil at the top, and basically showed how these very long wavelength, low frequency gravity waves are generated by that kind of forcing, and talked about what role they might play in the diurnal cycle. She's actually continuing that work for her PhD thesis now, and it turns out that gravity waves do have a role, but because of moist convection, the whole thing is actually a little bit more complicated. Was there a second part to that question?
So he asked, are the low-level gravity wave related to the upper-level stratosphere gravity wave?
Yes, right. So basically, at the same time, these waves are propagating upwards, and that is a topic of some research. If you want to follow up on that, there's a paper that I'm a co-author in BAMS from 2018 or 2019 about the GHOST satellite instrument, which was never launched, but that's a starting point for that. But yes, the waves they're basically, hurricanes are definitely making gravity waves that go up into the stratosphere. And as I said at the beginning of the talk, that's kind of like, that's a whole other research area, which I didn't get to talk about today.
Okay, and a question or comment from Brian Melody. He said, regarding the 1-minute geostationary image question, such data can be found online, and he gave a link in the Q&A chat.
Okay.
But he said he wondered if the strooping would be a problem.
I don't think so, right? So by strobing, you mean basically the data not being taken often enough, right? Is that what he's referring to? I have to say I'm not expert on satellite data. But I asked that person just to email me, and we can discuss it.
Here are actually some more questions in the chat, and one is from Will Miller, and he's asked, has anyone looked at how concentric eyewalls might modulate this gravity wave signal?
No, that's a good question. We don't know the answer to that. I like, for example, if I wanted to make observations of these waves, I would want there to not be a concentric eyewall, because I suspect that might, like, I don't know if the waves can get through, like if they're coming from the inner eyewall, would they get through the outer eyewall, or would they form on the outer eyewall, and would they be rotating so slowly then that you wouldn't really be able to see them? And in the case of this summer, when that Hurricane Teddy flight we were concerned that there was going to be a secondary eyewall, and I don't think there was actually in the end. So we were hoping that there wouldn't be.
All right. And here is another one from Junhu Singh. He said, according to Molina Real's study, the turbulence exists in the vicinity of tropical cyclones outflow layer. Do you think it is caused by the upper level gravity wave of the tropical cyclones?
No, I think that turbulence would be there even if there weren't the waves. You know, so if I go back to this, you know, you have like this very strong outflow. So the outflow, the upper level outflow in a hurricane is fast. You know, it's anywhere from 10 to 25 meters per second. And you have some areas of low stability there, and you have clouds and so on. So there's a lot of other good reasons for turbulence in the outflow layer. So I think the gravity waves that you can kind of see here in this image are just, you know, an oscillation in addition to that, but I don't think that they're the cause of the turbulence.
All right. So any other questions?
Oh, no, I thought you were asking me.
All right. So any other questions? If not, we are about to ramp up. And again, we thank the speaker for this great presentation. And we thank you all for coming. And we have our regular seminar next Monday. And you are welcome to come back.
All right, everyone, thanks for listening. I know that you're all clapping furiously right now, so thank you.
For the record, I was clapping.
Oh, good, good, okay. Okay, that's it?
Yeah,
Yes, that's
thanks.
it. Thank you so much.
Oh, you're welcome. All right, that was challenging, but I think I got the hang of it in the end there. So, all right, well, thanks for the opportunity. Thanks for the opportunity, guys. I appreciate it.
Yeah, so we got 41 attendees.
Oh, pretty good, pretty good. Okay. All right, bye, everyone.
Have a good one.
Have a good one.